We're ready to talk about a crazy useful reaction known as the Wittig reaction. Looks like Wittig, pronounced like Wittig, obviously a German individual. And one of the greatest things about this is it gives us access to all kinds of different alkenes that we can then use in a synthesis to do all kinds of crazy things too that we've already talked about a bunch. So this is specific to aldehydes and ketones. And so anywhere that we see a double bonded oxygen here, a carbonyl. Let's just start off with a really simple aldehyde here. What we can do is treat this thing with a very obvious Wittig reagent. It almost always, at some point, involves this crazy looking species, which is known as a phosphorus ylide. An ylide, I should probably write that down. An ylide is something that has both a negative and a positive charge right next to each other. And we know that generally that's something that's unstable, but in this particular case, that instability is something that we're going to take advantage of in order to get a reaction to happen. And so what we're going to do is we're going to notice that anytime we have a phosphorus ylide, by the way, there's another resonance form where this thing looks like this, but I don't think it's as easy to kind of see the reactivity pattern of an ylide. And we end up with whatever carbon with its R groups out here. I put H's, but these could just as easily be some sort of alkyl groups. We essentially take the carbonyl and replace it with whatever that carbon happens to be. These happen in really high yield, they're pretty easy to work with, and it's a really spectacular way to get to a brand new carbon-carbon bond. What we will talk a little bit about is how we actually produce something like this, and of course it's not that difficult, and so let's just take a look at that. So the first thing we're going to do is we're going to take a look at the group that we'd like to add here. Of course, I just picked out a really simple methylene group. And we're going to figure out what we need by adding a hydrogen wherever the minus charge is and an additional halide. And you'll kind of see where I'm going with this in just a second. So we are going to, since we want to add this component, we're going to put an H on there, right? An additional H that we're going to rip off eventually. And we're going to put some sort of halogen on there, right? And let's just say that it's a bromine, could be a chlorine, iodine, et cetera, et cetera. So the very first thing that we're going to do is we are going to pretty much treat this with a really, really strong nucleophile, right? Obviously this step of the reaction, because it truly is an SN2 type reaction, operates according to all those rules we talked about with SN2. So you may see problems with producing an ylide component where you have a really, really hindered carbon right here. But keep in mind that just like when we said, is this a good nucleophile, and we asked, is there a minus charge or a nitrogen present? Nitrogen and phosphorus are both in the same pnictogen family, so phosphorus is a spectacular nucleophile as well. And so what happens is this SN2 reaction. Oops, I didn't show my electron pair. I should probably show that. This sucker reaches out, does a backside attack just like we'd expect in an SN2. And at that point, we've got very, very close to our ylide. Very next thing that we're going to have to do is to treat this thing with a really, really, really strong base. Keep in mind, we talked about some organometallic reagents, specifically Grignards, and I said that those things really like to act as bases as well as nucleophiles. Well, it turns out there's a whole other set of reagents that are all based on organolithium chemistry. And so what we're going to do is we're going to treat this thing with something called N-butyl lithium, which is abbreviated like that. Sometimes you'll just see it written out like this. But N-butyl lithium is a spectacularly strong base that is going to be able to remove this hydrogen. Of course, the production of a minus charge right next to a plus charge, like I said, is a pretty unstable thing, so we need a really, really strong base to be able to do that. So just like we saw before with Grignards, Anytime that I see an organolithium, what I really think about it as is a functional equivalent of a carbanion, right? Even though it's often drawn as the covalent form. And so this thing is going to do just a normal old acid-base reaction. And we're going to have successfully formed our phosphorus ylide that we can then use in whatever reaction we'd like to do. So what I'm going to show you next is the mechanism for this process going from here to here, and we can pretty much call it a quick day. So this is one of those concerted reaction mechanisms that does have a little bit of beauty to it. And so what we're going to do in our mechanism is we're going to have this really strongly nucleophilic carbon reach in and directly attack. But instead of just flipping the electron pair up like we normally would, what we're going to do is we're going to reach over and attack this phosphorus. And so what we're going to have is an intermediate that looks like a square. And one of the things you'll notice is that this triphenylphosphine is actually bonded 5 times, right? It's hypervalent. That's one of the reasons that it has to be a phosphorus, is that it has those available d orbitals to actually go through a transition state that looks like this. And it's a pretty sweet mechanism here, because the next thing that happens is simply that these bonds undergo this kind of little mini paracyclic thing, and what we end up with is in fact our product. And of course, one of the things you consistently fish out of these Wittig reactions that can kind of sometimes be a pain, we have this really clean way of getting to double bonds. I will say I'm pretty sure, and I may be making this up, but I'm pretty sure another odd thing about this reaction is it actually prefers the cis orientation. If we were to have like a single R group on here, I'm pretty sure that the cis product is preferred, which is the exact opposite of what we would have to do to produce some sort of like E2 reaction. So add this one as a note card. It's a great reaction.